Somebody's coming? Okay. Sorry for that. Good afternoon to one and all, and a warm welcome to this inaugural function of the online course on emerging trends in biophysics. A special welcome to our chief guest, Professor Jayant Udgaonkar, Director ISAR Pune, and hearty welcome to Professor Gautam Bhattacharya, Director SINP, to Professor Abhijit Chakraborty and Professor Partho Saha, course coordinators, and to other senior faculty members from our CIU OCC, and of course to my dear participants. This pandemic has taught us many lessons, and one of those is learning through online course. In fact, blended learning has emerged as a buzzword as the way of learning in future. Now I invite Professor Rao, Chancellor of HBNI, for his welcome remarks. Sir, please.
Very good afternoon to everybody, and I would like to add my own words of welcome to Professor Jayant Udgaonkar, Director ISAR Pune, Professor Gautam Bhattacharya, Professor Prasanna Venkatraman, and many other faculty members and BOS members from HBNI who have joined. I think Director BRC, Professor Mohanty, also is planned to join shortly. So it's nice to meet so many of you in this program. And it's very heartening that a good number of students have joined for this course. I want to just make a few remarks in addition to welcoming everybody for this program. Some of the students, I know I've seen the profile of the students, they are not all from DAE. There are a good number of students who are also from outside DAE. So I want to welcome all of them to HBNI program. And I want to inform that one of the mandates of HBNI, rather I should talk about two mandates. First is to integrate academic programs across the constituent institutions of HBNI and the grant and aid institutes, which all, about 11 institutions which form part of HBNI. Each of these institutions, starting from BRC, IGCAR and others to SANP, VCC, IMSC, and so on, each of them has its own strength, its own tradition and culture, and its own excellence with regard to academic programs. And many of them run very unique programs. So for a long time, our thinking and effort has been how students from all these 11 institutes can benefit from special lectures and special research facilities available in all other institutes as well, because they are all under one single umbrella of HBNI. But I must say with a lot of happiness that by seeing the participants list in this program, this has been enabled by the information technology, and thanks to pandemic, we have been able to adopt this format. And I'm very happy that out of 11 constituent institutions and off-campus center of HBNI, 8 are represented, 8 students from 8 of those are participating in this. So this itself is a very good step that I find students from NICER, a very large number of students from RRCAT. In fact, after BRC, the next largest participant list is from RRCAT. I think 16 students are participating from RRCAT. So obviously we are taking the subject knowledge and expertise of Professor Abhijit Chakraborty and Professor Partho Saha from the east side to the west side, so all the way, and students are able to join from across the country, from all the constituent institutions. So this is a matter of great pride for us that this course has been unique. Obviously, it has also attracted very good participation from several institutions because of the eminence of the biophysics activities and the group at SINP. And I must record my sincere thanks to Professor Gautam Bhattacharya, who really conceived this idea and informed me that we can run this program, and very voluntarily came forward that this could be organized across the CIs by HBNI. So my thanks to Professor Gautam Bhattacharya and also Professor Abhijit Chakraborty and Professor Partho Saha, who have put in a lot of efforts along with Professor Maiti from here in designing the program, identifying the lecturers, and so on. Now, second part I want to mention is also that as the name of our university indicates, it is a Homi Bhabha National Institute. I always emphasize that this national word is very, very important. We are obliged to provide the best of the knowledge and expertise that our constituent institutions possess to every student in the country when if he can be connected or if he is willing to listen or learn from us. In fact, our rules also mention that the university is open to all, and anyone can join us and listen to the lectures. That is why we have made it publicly on YouTube, and all the lectures are also being archived on the YouTube. So if your students want to go back to some other courses like the one which we had on neutrons as probe for condensed matter, we have had several programs like this. All of these are available in YouTube if students go under HBNI webinar. So I want to mention this national character of HBNI is very important, and I'm happy that students from across the country are joining us. You are most welcome. And to those senior faculty members who have joined from different institutes, I want to mention that we will be most happy to welcome any ideas for future courses like this as well, which can benefit from students, benefit students across the CIs and across even the country. I'm sure there's a lot of scope for many such programs. We already have ideas for a few programs, and these are not necessarily only about science. They can also be about research methodology. They can also be about how to become entrepreneurs. They can be also about communications and opportunities for research across the country and across the world. There are several possibilities where we have experts from so many institutions across. We can bring them together and then help the students to learn much more. So we are definitely with everyone in this endeavor, and we keenly look forward to all suggestions. So with these few brief remarks, I once again welcome all of you to this event, and I hope that this course is a very good success and will get augmented by additional courses in the years to come. Thank you very much.
Thank you, sir. Now it's my pleasure to invite Professor Gautam Bhattacharya, Director SINP, for his introductory remarks. Professor Bhattacharya, please.
Yeah. Hello, everybody. I'm extremely pleased that SINP could contribute to HBNI's endeavor in reaching out to students across the country for imparting highly specialized technical knowledge through these online courses. Now, as Professor Maiti mentioned, difficult periods teach us things that we may not learn otherwise. Online teaching is one such example. One may argue that it is not as effective as in-person teaching, but who disagree that this helped us, bring experts and students from across the globe in the last 1.5 years that we couldn't otherwise have done. We couldn't have done it under one umbrella, and its benefit can go to a much wider audience, to a much wider, populace of a subject area. Now at SINP, we have a rather young and enthusiastic set of scientists in the biophysical science group with about 15 odd faculties. Around 10 of them are below the age of 50 years, with approximately 40 plus students and several postdocs. Now, in spite of their different areas of expertise, of late they are working under the thematically unified area of cancer-related research, under one umbrella. That's a good thing. Now, ours is one of the oldest biophysics group, started by Professor Meghnad Saha in the 1940s in the Calcutta University campus, in the Rajabajar Science College campus. Now, during 1946 to 48, during those 2 years, Professor N.N. Dasgupta, who was handpicked by Saha, indigenously fabricated an electron microscope and carried out path-breaking research on microscopic characterization of microorganisms and cellular architectures. Now, this, particular, piece, like, it's not very long, but still it oozes a lot of history. It is now a showpiece event in our exhibition gallery, this electron microscope. Now, post-MSc in bioscience started in 1973, coordinated by Professor N.N. Saha, who had nothing to do with Professor M.N. Saha. Now, you should remember that our post-MSc in physics program started in 1953, but the bioscience post-MSc started in 1973. Now, many of our bioscience alumni could be found within the country and outside in different academic organizations. Now, the online course on emerging trends in biophysics will continue during August for 3 months or 4 months, August to November this year. 10 of our colleagues and one colleague from ACTREC will deliver 43 lectures, each 1 hour. And I have been told that about 90 students, and just now I heard about 95 students from across the country, from DAE or non-DAE organizations, universities, ICERTs from different places, IITs, have registered for this course. Now, my best wishes to all of them. Now, my special thanks on behalf of my entire fraternity of SINP to Professor Abhijit Chakraborty and Professor Partho Saha for chalking out this program. In fact, conceiving the program with inspiration from Professor Dilip Maiki of HBNI. Now, I recall that in one of the valedictory ceremony of a previous course, if I remember correctly, it was on some nuclear science course I don't exactly remember the name of the course, but it one of the nuclear science course. Professor Dilip Maiki suggested that SINP could think of organizing, a course like that. I mean, which would help, students from across the country. And I must say that it was not me, but Professor Dilip Maiti who projected this idea, and Professor Abhijit Chakraborty and Professor Partho Saha gave a shape to this entire course. Now, finally, my very special thanks to Professor Vasudeva Rao and his team for giving us this opportunity, and Professor Jayant Udgaonkar for gracing this occasion. Now, thank you very much.
Thank you, Professor Gautam Bhattacharya, for nice words and talking about the history or genesis of this biophysics course in SINP, which has a long history. Well, now I invite Professor Abhijit Chakraborty and Professor Partho Saha, two course coordinators of this course. Please, they will talk about the course and the credit. Many participants will be interested to earn credit also based on this course. So what are the rules and intricacies, how the exam will be conducted, all these things will be talked about by them. I request them to.
So can you hear me? This is Abhijit Chakraborty.
Yes, we can hear you.
Yeah. So before this presentation gets sorted out, so I would just like to first thing is hello to Professor Vasudeva Rao, Jayant, and Dilip Maiti, Gautam, my director, and Prasanna, my dear friend. Now, this Prasanna happens to be the convener of the Board of Studies of Life Science in HBNI. And these days, you probably know that, getting a support for a biophysics course, it was, as Gautam mentioned, in early years, Shah Institute started, Meghnad Shah started in, I would say, around late 50s, though that electron microscopy story that basically started. But even if then, the Bangalore group, this MBU, so all biophysics activities in this country, it was, I would say, at the peak in 70s and 80s. And then, pardon me if I'm, bit too much on this issue. Then we saw somehow, at least this younger people and younger, I mean faculty and students both. Then we saw a kind of a decline for whatever reason. that people are no more interested in, well, I won't say interested, but at least it was less glamorous, it became. Now, the good news is I could see, and probably all of us can see, there is some kind of a, some kind of a I mean, interest is again kind of pouring in. Now, whatever may be the reason, maybe due to these newer techniques, there are fascinating areas of research and so on and so forth. So we have all kind of been noticing that again, probably so-called biophysics, biochemistry, chemical biology together, these areas are getting more, getting more encouragements from the younger colleagues as well as the students. Now, that is basically is the background. And what we have, just now Professor Bhattacharya mentioned that we have a bunch of, a reasonable bunch of young colleagues who are, many of them are really working on using cutting edge technologies like, mass spectrometry, single molecule spectroscopy, biology. Even we have a bioengineering person who basically their approach is to take a biological system as an engineering system. So the gene circuitry and all those issues, synthetic biology that he talks about. So all these thing is happening. At least people like me, a 60 plus, in front of my is, I would say, past 5-6 years. And lo and behold, Dilip, my good friend, in that valedictory session, he says, why not offer a course on biophysics? And so that is the genesis of this course, what we call as emerging trends in biophysics. And our, Partho will soon tell you what all it contains and what all is there. It is also there in the slides. I'm not just going through them. You all know it is a bit of technique based, but it is unless you learn the language, it could be difficult for you. Now, this you meaning mostly the students. I'm very happy to see about close to 60 students will be participating in this. 55 or 56 probably is the exact number. And there are younger faculty members, and more importantly, which I think, this is a discipline which is the best possible, so-called example of interdisciplinary science. But chemists and physicists has to come back. I somehow have a feeling that there was, or there is probably, is probably they have to kind of come back and give it a try on this field of biophysics. And similarly, I can see there are lots of life science people. We have just kept one thing here, and probably I mention it, and that is, we at least expect all these young students of mine who will be taking this course seriously. They would like to get the credit out of it. Then, we have kind of our intention was that at least they should brush up their higher secondary level physics and mathematics knowledge before they get into this course. So this much is from my end, and now I would say Partho can go through the real content of the course. So thank you, Jayant, for your time. Thank you, Prasanna. Prasanna, I have insisted hard, and she has also agreed that she will also be talking about a bit of protein-protein interactions and some of the mass spectrometry issues in structural biology in two of our lectures, which are also coming up. So it's basically a 90% Shaha Institute, but there is V. Prasanna. She will also have two lectures out of this. So here I stop.
Thanks, Abhijit. I'm very happy to be part of it. And I'll also be sitting along with the students to listen to the rest of the lectures.
Thank you.
Okay, thank you, Professor Chakravarti. Abhijit, thank you very much. Yeah, now Professor Saha will be talking. Partha Saha. Yeah.
Could you see the presentation? Is it?
Yeah, we can see that.
Okay. Next slide.
So this one. Yeah.
Okay, so I'll just give you a brief overview of the topics which will be covered in the course of lectures. There will be 11 faculty members who will be delivering the lectures, and 10 of them are from Shaha Institute, and Professor V. Prasanna from ACTREC. Professor Shubhabrata Majumdar will start with multi-dimensional NMR, in which he will discuss 1D and 2D NMR as diagnostic structural method for proteins, improving dynamics, utility in analyzing high molecular weight proteins, and most interestingly, in-cell NMR. Then Professor Soumen Kanti Manna will discuss on mass spectrometry for structural analysis of macromolecules, followed by a course of 2 lectures by Professor V. Prasanna from ACTREC on applications of mass spectrometry for structure determination and protein interaction. Macromolecular crystallography will be the next topic, which will be delivered by Udayaditya Sen, and that will also include a 1-hour demonstration. Then Professor Raghu Raman will discuss on pulsed electron paramagnetic resonance application in proteins. Multi-scale modeling and simulation of biological system will be discussed by Shubhendu Rai in course of 4 lectures. He will cover advanced simulation techniques, including hybrid QM and MMMD simulation, and simulating chemical reactions of biomolecules. Next, Professor Padmaja Prasad Misra will cover single molecule spectroscopy, comprising fluorescence correlation spectroscopy, optical tweezers, single molecule FRET imaging, and this will also include a 1-hour demonstration. Professor Raghuraman will come back with his course of lectures on membrane biophysics and membrane proteins. He will discuss on models of biomembrane organization, membrane mimetic systems, lipid-protein interactions, and membrane structural biology, which is always a challenging field. X-ray and neutron scattering application will be discussed by Professor Minmoy Mukhopadhyay. He will give lectures on basic understanding complementary role of X-ray and neutron reflectivity and its importance in biology. After this, we'll cover many important topics in modern life science. Like Soumen Kanti Manna will give a course of lectures on mass spectrometry and omics, including metabolomics, lipidomics, and proteomics. Professor Sangram Bag will deliver lectures on space bioengineering and synthetic biology. He will discuss on correlation between electronic and gene regulatory networks and its application in designing novel biological functions. Application of synthetic biology in energy materials space travel, medicine, and computation will also be covered by Professor Sangram Bag. Mechanotransaction in cells, biochemical signaling, and gene expression will be discussed by Professor Kaushik Sengupta in his Mechanobiophysics course. Last but not the least, Professor Dural Senapati will discuss on nanobiophysics, which will include fabrication and characterization of nanobiomaterials and application in sensing, quantification, and therapeutics. These have already been discussed by Professor Rao. The total number of participants are 95, and they are from DAE as well as non-DAE institute and universities, and from all over India. I'll just discuss some important information for participants. Like at least 75% attendance in the lectures are required for the participants who like to receive participation certificate. We will conduct evaluation of the participants that will be based on regular assignments.
Somehow slide is not changed. Slide changing is not done. Slide is not changed.
But I have changed here.
But today's network is not good. I mean,
You need to.
Now we are seeing. We are seeing now.
Okay.
Now it has come.
yes. Now it's okay. Now it's okay.
Now it's come. Now it's come.
Fine. Okay. So participants who want to receive participation certificate need to attend at least 75% of the lectures, and we will carry out evaluation of the participants by regular assignments and one in-semester quiz and one end-semester examination. Students who wish to get credit for the course, this course will carry 6 credit. So who want credit for the course need to attend a minimum of 75% of the lectures, submit the assignments, and appear for in-semester and end-semester quiz and examination, and secure more than 50% overall marks. So participant will get some username and password that will be emailed to every participant for logging in to attend the lectures at Anuvidya website. For the next class, I think they will provide the link in the Anuvidya site, and then they will receive the login name and password. And lectures and assignments, questions that will be uploaded in the website, Anuvidya website, and a dedicated email account have been created, like etb2021.hbni@gmail.com. We will share the questions and assignments there, and participants can send their queries, feedbacks, and submission of assignments to that email. Participants may also use the chat mode to post their queries during the lectures. So participants are requested to keep their audio muted when the lectures are in progress, and it is very important that all participants must mention the code assigned to them by HBNI in chat mode to register their attendance. So I think the course will be very enjoyable. Participants will enjoy the course, and all the teachers they are very young. Most of the teachers are very young, and they are expert in their field. Please interact with them and enjoy the course. All the best. Thank you.
Thank you, Professor Saha and Professor Chakraborty, about the course. And the students, if you have any further queries, you can send an email to that email, whatever Professor Saha mentioned, and you will get the answer. More details also have been, I think, already emailed to them about how to go about the attendance part and login and password. Already they have been forwarded about their even registration number has been also emailed by our IT person, Mr. Anurag Sharma. He has already sent it, but if needed, we will send it again. And for the next lecture, that is the Tuesday's lecture, you can get the link directly connecting through Anuvidya, or we are also sending the link to you direct email, but because that is the first lecture. Then onwards, we will change the thing. Okay, now it's my pleasure to invite Professor Jayant Udgaonkar, Director ISAR Pune, to have words with the students for encourage them to attend this course. Thank you. Professor Udgaonkar, please.
Hello. Hi, so it's my privilege to talk at this inaugural function of the workshop. I'm very happy that the HPNI has organized this workshop, and the program looks very interesting, covering many of the methodologies which are used for research in biophysics today. So what I will do in the next 5-10 minutes is really talk to you about what biophysics is supposed to achieve and what we would like to see it achieve. Now, when I started doing my PhD, this was at Cornell University in the USA, I joined a laboratory which looked at the functioning of neurotransmitter receptors. These are receptors which carry messages from one neuron to another, or neuron to muscle in your body. And my laboratory was a biochemistry laboratory, a biochemistry department, but it was situated in the applied physics department. And part of the reason was because of the methodologies which the laboratory used, which were rapid mixing methods to study problems of biological interest. So you would probably know that the invention of methods such as temperature jump, etc., really revolutionized the study of enzyme function, because they allowed enzyme studies to be carried out in the time domain where they really carried out their function. Now, in my first few months in that laboratory, an eminent biophysicist walked into the lab, not my advisor, but another one from another lab, and a very friendly guy. And he started talking about biophysicists. And he said, you know, a biophysicist is someone who talks biology to physics, physicists, and physics to biologists, can really then get away with saying anything he or she wants to say. And actually, in my experience of the last 30 odd years, that is true in many, many cases, but not in all cases. Now, as I mentioned, my laboratory was situated in the applied physics department, but my PhD advisor didn't consider himself to be a biophysicist. And in fact, when I tried to use the word biophysical studies in my thesis title, he refused to allow that. He said he wouldn't sign my thesis if I put the word biophysical in the title. And he said he's not a biophysicist, so how could any work in his lab be biophysical in nature? My work at that time used two of the most important methods in biophysics of that time, rapid kinetic methods as well as single channel recording, which was what the first single molecule method used in biology. Nevertheless, what was important in his thinking was not the method, but the thinking which goes behind looking at a problem. And he looked at himself more as a physical chemist rather than a biophysicist. There are subtle differences between the two, and I've kind of imbibed this way of thinking. So for roughly 30 years, I've been teaching a course which most people would consider as a biophysics course, but I have insisted on calling it a physical biochemistry course because the thinking, even though the methodologies are those perhaps of biophysicists, the thinking is more, which I try to introduce to the students, is more of a physical chemist. Nevertheless, because I have been teaching this course and because the methodologies my laboratory has been using over the last 30 years would qualify as biophysical methodologies, including several of the methodologies which are covered in this workshop, which will be covered in this workshop. I think I have enough expertise in biophysics to talk about what the role of biophysics is in the study of biology. And so what I'll do in the next 5 minutes really is talk about how useful biophysics could be, and is it to address the question of whether it really is useful in the study of living matter. So we know that the study of living matter, biology, is probably one of the most exciting frontier areas in science. I don't think there's probably not any one of us who has not wondered how our brains work, for example. And how does the biophysicists and biophysics help in addressing the question of how biological processes work, how living things work? Now, there is, unlike other areas of physics, biophysics has to address the question of not how things might work, but how things actually do work. And there's a subtle difference there, because you want to know how your biological processes are actually working, not how they might be working. So the question then arises, does biology require physics? Does it require thinking of physicists, which physicists think in very different ways than do biologists? And so does biology require physics? Biology has its foundations in biochemistry and genetics, and not really in quantitative thinking, which is associated with a physicist. And so the methods of biophysics, methods of physics are, of course, of great importance and utility in biology. So we all know them. They're all being covered. Most of them are being covered in this workshop. And most of these uses of physics have been in terms of instrumentation, microscopy, spectroscopy, single molecule methods, specialized imaging methods, specialized methods for measuring currents in your body, etc. But what's more important is, does biophysics help in thinking in biology? Now, my first course in biophysics when I was a PhD student was taught by a very well-known biophysicist, Watt Webb. It's in his lab that methods such as fluorescence correlation spectroscopy and multiphoton spectroscopy were developed, microscopy and spectroscopy were developed. And he taught this course, and he brought out, I remember quite well, the question of how do molecules go from one end of a neuron in your spinal cord, which starts in your spinal cord, to the end of your foot, which is a distance of more than a meter for many people. Obviously, he made the point, and in terms of how a physicist would think, can go by diffusion, and you can easily calculate using simple physics equations that it cannot in a biologically relevant time scale. And then he brought out the importance then of there had to be an active transport system. This was at a time when the molecules involved in active transport were not really identified. And so it can help thinking. This is just a very small example. We have to realize that biology is constrained by the context of evolutionary history, the context of everything having developed in a water environment of in a very narrow temperature range. And physics hopefully can help in understanding what these constraints do in our understanding of biological processes. So what do we want physics to do? We want physics or biophysics to come up with unifying principles in biology. And that's very important, because in biology, there's so much diversity. And how does one understand that diversity? How do you get unifying principles when there's so much variety in shape, structure, form, function from one end of the biological spectrum to the other? And perhaps the biggest contribution a biophysicist can make is in linking large amounts of data, quantitative biological data, to one another, through simple concepts and simple models. And that is happening more and more, and it's happened more in the last 10, 20 years as more and more physicists have gotten into looking at problems of biology. And this is very important because biology is essentially, to a very large extent, the collection of lots and lots and lots of data. And how does one understand these very large amounts of data? You know, you could argue, for example, that Darwin could come up with his theory of evolution because he had a limited amount of data to study. If he were present in the current time and had to develop this theory now, would he have been overwhelmed by the quantity of data? How do you sieve through large amounts of data? And that's where simple models can help. And these models have to come from physicists and from biophysicists. You know, biologists revel in the complexities of the problems they study. You know, but the problem there is then you have so much complexity, you don't know what is important. You do a proteomic study or a lipidomic study, you'll understand, you'll identify 50 or 100 or 1,000 molecules involved in something, but you don't really know what is important. How do you come up with minimal models which will tell you how to explain the biological phenomenon which you are studying? And that's where the tools of biophysics, the physics and the chemistry and the computational methods and the mathematical methods come into play. So we need simple models. So because you want to understand things at some basic level, simple models very often will not explain all the data, which it's not necessary that models have to explain all the data. You know, all data for any particular phenomenon may not be correct, may not have been correctly acquired. And Francis Crick is reported to have said at one time, I'm not sure it was him, but he's been quoted as saying that any model which explains all the data cannot be correct because all the data is never correct. So, but nevertheless, you want models which can explain large fractions of the data. These models would always evolve as more and more data is collected, biological data is collected, and then one understands biological phenomena better and better. Theory in physics is, of course, of great importance. Theory in biology is very difficult to come by. Statistical mechanics, of course, has been of great help in understanding biological processes. And because statistical mechanics is probably the most useful theory in physics, perhaps, and certainly in biology and chemistry. But if you want theory to be useful in biology, it has to be able to make useful predictions. You do not want a theory which can accommodate data, because then you don't really learn anything new. In my own area of protein folding, energy landscape theory can accommodate data. It can account for data for many different proteins, but it's not that useful in predicting what is actually happening for any given system. So you want theories which can make testable predictions. And again, this is an area where biophysicists can play a big role. So of course, biophysicists come in two flavors. There's the type who develop instrumentation, and then there are the ones who use these methods to get quantitative data on a particular problem. Now, so, you know, if a student wants to get into instrument building can be quite complicated, can take time. One should never lose sight of the problem you want to work on. If you want to this is meant now more for the students. So if you want to become an instrumentation person, it's not enough to just develop an instrument once. You have to keep, you know, upgrading it. You have to keep making it so that it is always state of the art. Because, you know, you're going to be competing with commercial instruments, and there's no point using a home-built instrument to study a complex process when your home-built instrument is generation 1, whereas a commercial instrument is generation 10. You will never get the quality of data which might be necessary for studying the problem you have. So you have to then keep building, keep developing new instruments while still, keeping sight of the problem. Now, the problem which is there all over the world is that very often you have to spend so much time developing an instrument that your entire energy goes into that, your entire thinking goes into that, that once you build the instrument, very often a biophysicist is at loss to what problem to work on. And this is something which that's why I said it's important that the biophysicists keep in touch with the problem, because the problem is what should be motivating the biophysicists to develop the instrument in the first place. So the other problem I've seen is that many biophysicists tend to be wedded to one methodology. But problems in biology are complicated. And if you want to be a successful biophysicist, you have to understand what is the best instrument, what is the best technique to look at the problem which you are interested in. Remember that the problem must select the technique should not select the problem. So biophysicists, of course, should be choosing problems which are biological interest, and they should have some idea of how biophysical methods or biophysical thinking can help in contributing to a basic understanding of the biological process. What level of detail is necessary for understanding a biological process? Can modeling help by suggesting further experiments, for example, or telling you that this part of your data or this part of your data is not important? And for example, for people doing simulations, simulations can become more and more and more complicated. You can keep adding parameters, but will they contribute to understanding a process? For example, to me, simulations can be of most use when they tell you X and Y and Z are not important for understanding a biological process, rather than telling you that A and B and C are important. And so these are things which involve, a way of thinking which a biophysicist needs to develop. So thinking about which problem you want to work on, again, this is meant for students, is something very important, something you want to work on an emergent or emerging problem. Techniques will keep coming up, new and newer techniques, so you'll have to keep learning newer and newer methods as they come across. And you need to really decide on what is an important problem. So I've been working primarily in one problem for the last 30 odd years, the problem of protein folding. This is probably the most multidisciplinary problem in science even now. You have physicists, chemists, biologists, mathematicians, computer scientists, virtually any science you can think of is involved in the study of protein folding. And again, the level of understanding is still not adequate. And recently there was an AI program, artificial intelligence program, AlphaFold, which made very good predictions of protein structure. And that's one facet of the protein folding problem. How do you predict structure from sequence? The other facet is what we are interested in, is what is the mechanism of folding. So now we know that artificial intelligence can understand protein folding to some extent, but can the computer explain to us how proteins fold? They cannot. So one has to still figure out how things work in using the methods of biophysics, the thinking of biophysics, etc., to understand very simple, complicated processes in biology. So one of the very trendy emerging areas in biology today is the study of phase separation in cells. It's been recognized now that just like oil drops phase separate in water, many proteins phase separate, proteins and other biomolecules associated with proteins phase separate in water. And give rise to what are called membraneless organelles inside the cell. And what is the role of biophysics in this trendy emerging area? How does one understand how these molecules are associating with each other when they phase separate? What are the type of interactions stabilizing them? Because to have phase separation, you need enthalpic interactions which overcome entropic costs. And so these are things where this is an area where biophysicists can contribute a lot. So lastly, I just want to make the point about biophysics in the test tube or in vitro versus biophysics in the cell versus biophysics in the tissue versus biophysics in the organism. So, most biophysics is done in the test tube. You work with purified solutions, purified molecules, and you try to understand what are the different ways in which a biological system can work. Obviously, in the cell or in the organism or in the tissue, one of those many ways of a biological system can work in a test tube will work in the cell. Now, many biologists will say the cell is the best system to work, but cells to me are badly defined test tubes. And nevertheless, it's important to develop methodologies which are only now in the last 10 years being developed to study biological processes using many of the methods which you will be learning about in this course. And, that's where a frontier area in biophysics, developing the methodologies which allow you to do the same measurements inside the cell as you can use outside the cell. Things should not be very different because the laws of chemistry and physics are the same wherever you are. And given what we know about the environment inside a cell, one can predict a lot about how biological processes will be in the cell from what you know how they occur outside the cell. So that's about all I have to say. I'm very happy that there's a workshop which has been organized, and I'm sure the students will learn a lot. And it's again, thank you very much for listening to me mumbling along. Thank you.
Thank you, Professor Udgam, for a wonderful presentation you made, and nicely bringing out what is biophysics, how it evolved from say in last 3 decades, and what are the emerging areas, and what is expected from a future biophysicist. So thank you very much, sir, for giving us time and accepting our invitation very readily and giving this time. Thank you, sir. Now it's my pleasure to present duty to propose vote of thanks. I thank Professor Rao to take this wonderful initiative to tap the strengths of our faculty members in one campus and spreading it to all other 10 campuses and even to outside HBNI walls for the benefit of the students. Sincere thanks are also to Professor Bhattacharya, Professor Chakraborty, Professor Saha from SINP for putting all the efforts and all the teaching faculty members of this course. I extend my gratitude to all the members of Board of Studies Life Sciences for having a brainstorming session on the course structure proposed by SINP, and finally credit assignment. Most importantly, I thank all the participants of this course for their interest. I'm quite sure that you all are going to have a wonderful learning experience in the emerging areas of biophysics. Sincere thanks are also due to Mr. Anurag, Mr. Rishabh, our IT people, and Office of VC for their help and all the arrangements. Thank you all. So that brings a closing of this inaugural program. Thank you very much. Thank you, sir. Thank you, Professor Udganga. Thank you, sir.
Thank you. Hi, Sagram. How are you?